Okay, this is the last part on chapter 8, and it's going to be about the design of one-waist joist floor system. The section 9.8 in your code has all the information really available for this. It's not very much, but it has some key information that you guys need to remember. Okay. So here is this one, right? Okay. Yeah. So 9.8, non-pre-stressed one-way joist systems. And let me see if I can make it a little bigger here for you guys so you can see it. There it is. All right. And so it simply starts, by telling what it is, right? A non-pre-stressed one-way joist construction consists of a monolithic combination of regularly spaced ribs. Okay, this causes a little bit of a problem in terms of some definitions, okay? But that's what we call it, ribs, which are really the little beams, okay? So these are the little beams that you have, right? So you have those beams and the top is lap, designed to span in one direction, perpendicular to the joists. All right? So the joists are the support. Right? And then the commentary simply says that whatever limits are given here is based on experience. Okay? Width of ribs shall be at least 4 inches at any location along the depth. Okay? So they say along the left because in the US the ribs have a variable width. Okay? And therefore they want to make sure that the minimum value is 4 inches. Okay? Overall depth of the ribs shall not exceed 3.5 times the minimum depth. Okay? So 4 times 3.5. So that would be the maximum you can have with 4 inches. Okay? And so that's what they're recommending. But this is for standard joist systems. Okay? Clear spacing between ribs shall not exceed 30 inches. The clear spacing. So all this is for standard joist systems. If you have a skip joist system, right? Right. So then some of these things do not apply. Okay? Because you are going to have, for example, 6 feet probably center to center. Your clear spacing is not going to be 30. Okay? So this is a standard joist systems. Okay? V sub C shall be permitted to be taken as 1.1 times the value in 22.5. What that means simply is whatever formula we've been using for shear, right? That V sub C that you find, you can increase it by 10%. Okay? And this is again because based on experience, okay? And the fact that the beams are so closed, right, that any overload on one side can be taken by the rest of the joists, right? But the key is this. So standard joist systems. So if you have, again, a wide beam module or a skip joist module, this does not apply. Okay? So all this basically for regular standard joist systems. For structural integrity, at least one bottom bar in each joist shall be continuous and shall be anchored to develop Fy at the face of the supports. Okay? So that means that you have a joist that goes, say, 35 feet. One bar has to be, that long. Okay, 35 feet, and anchor the supports, so it will be able to take the tension and develop the Fy stress. Now, if you don't have that bar that are that long, you're still allowed to splice them, okay? But that makes it also continuous. You can do that through splices. So in the direction perpendicular to the joist, you may need to provide reinforcement. Okay, you had to provide this reinforcement, right? And that will be your bending of the slab, right? And you need to be able to take any load concentrations. Okay? The minimum you should use is the shrinkage and temperature value that we were using for the slabs. Okay, so it's the minimum value that you will use. Okay, so this one right here refers to the value in the slabs. Okay, so you go back here, so 24.4, right? Oops. Shrinkage and temperature reinforcement, right? So there it is. And moment, all this right here. Okay, so that one has to be provided. So where's the formula? Oh, in the next page. So right here. Okay. So that's the value that we were using, right? The 0.0018. So that's what they're talking about. All right. That work. So I had to go back to 9. All right, so 9.9, 9.9, okay, so close. So that's the reinforcement, yeah? Then one-way joist construction not satisfying the limitations of 9811 through 9814 shall be designed as slabs and beams. So basically you have a skip joist system, right? Then it will be like a regular beam design. The only thing you're taking advantage of is the shape of the joist. But you will have to design it like a regular beam and joist system. Okay. There are cases where you will use within the joists, right, in that space that is left between the joist, you may put basically bricks. Okay, so that's what this is: bricks or concrete tile fillers, or any other material having a compressive strength at least equal to F prime C in the joist. Right? Then you have these conditions. Slab thickness over fillers shall be at least the greater of 1/12 the clear distance between ribs and 1.5. Okay. For calculation of shear and negative moment strength, it shall be permitted to include the vertical shells of the fillers in contact with the ribs. Okay. So these units would be part of your calculation. Okay, so that's with fillers. And then we got the case with no fillers. If fillers not complying with 9821 or removable forms, which is what we do normally here in the US, slab thickness shall be at least the greater of 1/12 the clear distance between ribs and 2 inches. Okay, so this is what we're going to use. Let me see here. Let me do a little thing here. I haven't done this. Let me check joists, joist systems. No, that's the wrong one. I had to put concrete joist systems because otherwise you get all these timber joists, right? And so that will not work. So timber joists, okay, so here they are. Let's see what we can take here. This looks like the pictures I have and the notes. Let's see, images. So what do I want to show you here? for this. So you can see here the joists, I mean, right? So notice the section, trapezoidal, right? And that's because of the forms we use here in the US. So that's very important. So there's lots of information about that. So another picture of joists. These are the standard joists. These are the double joists in both directions. I show you some pictures of that, but that's not what I'm looking for. Okay, these are the ones I'm looking for, right? So these are kind of the old ones, see, where you put the clay units between the joists like that. That's one way. Some don't even have that support. They just attach with the mortar, and everything is attached that way. Okay? Here, for example, this is a good one to show you the type of reinforcement that you put in the joists. Usually, I mean, the easiest way to do this is with welded wire reinforcement. Okay? That would be one way of doing this. Here is another one. Let me see if I can get this one. Yeah, this is also antiquated. See, antiquated structural system, very old, right? So that's what the people used to do. They would put these brick units, right, and then your joists, right, in there. And so that's how it was designed. As I said, we here in the U.S. we don't do that, but in other countries they still do some of this. Okay. So those are also joists. Let me see if there is anything different other than this, something interesting here. They're all the same. Oh, these are the forms. Okay? These are your forms. Notice the form already set up, trapezoidal, and they have different lengths. So these are standard lengths. Okay? And so this will be your clear lengths. Okay? These are your clear values right in here. Okay? Because these are the metal forms that you're going to use already. Okay? And that's why you had to follow those dimensions. You cannot just pick anything you want. Okay? So you have clear distances of 20, 30, 45, 53, 66. So normally we're either 30 for a standard or 66 for a skip joist system. Okay? So that's what you will do. Let me see if we can get more of these. There, see. Okay, so that's kind of the metal joist system. Didn't go that way. Oh yeah. So that's what they are. I mean, these metal joist systems, they can be metal, they can be made of other plastic, like a polymer that is resistant because to take the pressure from the concrete, right? So that can be done that way. So these are the forms, okay? So you use these forms, they're specially designed that way, so that's why you had to pick those dimensions, okay? So here, for example, this one, let me see, here is from PCA. So PCA has lots of information, so that's why I wanted you to look at that. So here is the dimensions of the forms, right? And so how high you can get it, right? Plus the slab. So you still got your little slab that goes on top, right? Notice that the slope of this is 1 inch every foot. So that's how your slope is changing on that trapezoidal shape of your form, okay? So these are the typical joists, skip, and this is how the forms will look in the field before you pour the joists. So you put all these forms, and then you pour the concrete on top, okay? And so these are your 66 inches module, right? And that you can have. So again, let me see. So yeah, your white module form, so that notice the spacing is a little bigger. So see all these documents that you can look for and get that. Now you want a special heights, deeper, there are special forms too. And so this is the kind of material that you as an engineer will have to look for. Okay, I mean, I cannot give you all this. I mean, there's lots of stuff. Okay? But this is what you look for. Okay? And so that way you have the material to do your designs. Okay? So that's available. Okay, so let's move on that. And that's what I wanted to show you from the code. And so that's the code. And so let's go back to our design. And we can go here. So it is then a monolithic construction, meaning that you're going to pour the slab and the joist all at the same time. Okay? And everything will be one unit with your columns and any other beams that you may have, or walls. You have walls, right? This is the figure that we've seen already in the web, very similar, right? In there. Okay. And the only problem with that is the term ribs. Remember that the code used ribs to call the actual joists, right? They call them ribs, spaced at 30 inches. The problem with that is that really there is a true rib that you put in these joist systems, and it's this one right here. Okay, and that may confuse some people. Okay, so this rib is a special member that you put across the joists, and that's a true rib. So the name is really rib. Okay? But these ones are more properly called joists. Okay? So you got the joists and the rib. So when do you use this rib right here? One is required for spans between 20 feet to 30 feet. You should put one in the middle. Okay? And you will use two if you exceed the spans of 30 feet. Okay? And this will give you a better stability of the system. It allows you to distribute any concentrated loads to all the joists, right? And so that's a rib. Okay? But notice that at the same time, even PCA calls this a rib or joist slab, right? Because these are also called ribs. So that's what makes it confusing. Okay? But the true rib is this one, okay? Perpendicular to the joist. Okay? Normally you will have a very wide beam because, as I said, the height of the joist and the height of the beam will be the same. Okay? You will match that. And in order to carry your moment, because you cannot increase your height, you make it wider. Right? In there. Okay. So we already looked this into the code, right? Depending if you have fillers or not, it tells you how much is your thickness. Clay fillers can be used with a smaller spacing. Okay, so we're done with this. Normally you have a standard joist of 20 inches that you clear. I show you the 20, the 30, remember? 20, 30, 45, 53, and 66. Did I show you those forms? Okay, using those, 20 will be 2 inches, 30 will be about 2.5 inches. However, these are pretty small, so you have this exposed, right? Then durability and fire requirements may result in thicker values, right? So you may need a 4.5 inch slab. And this is why people move from the standard joist to the skip joist. Because if I'm going to put that slab at 4.5 or 5 inches, then why do I have to put my joist at 30 inches, you know? Now I can make wider spacing and take advantage of the thicker slab. All right. Now, the actual ribs that I mentioned here are not in the code. They are not mentioned in the code. This is just a recommendation from CRSide. Okay? And this is the Reinforcing Institute, Concrete Reinforcing Institute. Okay? Steel Institute, Concrete Reinforcing Steel Institute. Okay? And so that's what they have. And so you will have a distribution rib. That's what it is. Okay, that's a distribution rib. One for lengths over 20 feet up to 30, and then over 30 you will use two ribs. Okay. Joists can be designed with and without stirrups. So if you are not putting stirrups, then the you need to check the ends of the joists, because that's where you have your maximum shear, right? To be able to carry that without stirrups. And in most cases, it will not pass. And you will have to widen the joist at the ends. Mm-hmm. And there are forms already designed for that purpose. Okay? So those are also available. Okay? But with the new code, though, right, 2019 code, remember that we had two sets of formulas, right? One set when you satisfied AV minimum to calculate your shear, and another set when you do not satisfy AV minimum. So you do not put stirrups, you have to use the formula with no stirrups, meaning AV minimum not satisfied. Okay? And that changes now. Now that changes some of the designs of these joists. Currently, the people that write the code are looking at these special cases, joists, walls, footings, right, that are being affected by that new requirement, because that new requirement of having a one shear formula with AV minimum and another one with no AV minimum was developed for beams, but now it's affecting other elements. Okay, so that's being studied. I will not be surprised that maybe in a couple of years you will see some changes on that. Okay, so a typical joist system is being shown here. Okay, there it is. There is the slope that we talk about. Remember on the form, right? The different values of the heights depending on what module you are using. Okay, the 2 feet module, the 3 feet module, 4 feet module, and the 5 and 6. So normally you're looking at a skip joist we're going to use here, usually 6, and a typical standard will be 3. But there is 2 feet module. Okay? So for those of you that were worried about your spacing, remember in your project, right? You say, oh, well, it doesn't match exactly. Well, you could combine maybe a 3 with a 2. Okay, and you better a combination that right at the end. Okay? And then here is some of the clear spacings and what the B's are. So notice that the B minimum, remember the B minimum in the code, 4 inches, right? So these two satisfy standard joists. After that, all these are Y module joists and do not satisfy section 9.8. So all this right here, these 3 right here, have to be designed as regular beams. Okay. So your standard joist should be this right here, okay? And your skip joist system should satisfy this. Notice that the width starts at 6, so 6 will be here, okay? But here it will not be 6, right? Because if it goes 1 inch at 12, right? When you get here, let's say you only got 12 inches, that means that you start with 6, you already got 8 right in here. Okay. Okay, so these are the dimensions that you have to use in your joist system floor. Some typical details shown in 8.15. So here is some details. Okay, here is the reinforcement in the slab. You have both, this one and that one. And notice that this is put right in the middle. Okay? Right in the middle. Mm-hmm. So it's more like a tempered shrinkage right in the middle. It should be checked though to calculate any point loads. If you have any point loads, that needs to be checked for that. But then in that case, your D value, remember, is only to the middle, because that's where you are putting these bars. Okay. So be careful with that, because you are not putting this at the regular covers. Okay. So we had to satisfy any concentrated loads, but as a minimum you had to use ACI 318. We already look at it, right? The 0.0018, right? So 8 to 24 here, right? Bars could be 1 or 2 depending. You cannot put really more than 2 unless, I mean, you put it wider, so it doesn't make sense. These are the different modules that you can use. We already did that, right? The minimum width, remember, 4 inches. So we have that. Okay. This right here is a detail. Now you're looking at the joist longitudinal. So this is your joist. Right? This is your joist. And this is a beam. This is the case when the beam happens to be deeper than the joist. Okay? And they use this little gap here so you can pull the forms. Okay? You can take them out later. Okay? This one right here is your rib, your distribution rib. So it's like this. Okay, this is the plan view, and this is the vertical view. So this joist, the joist, and this one right here, right, is your rib, which is that one. The one number 4, top and bottom, you don't have to design it, you just put it in. Okay, but that's typical. Okay? Here it just shows you the different lines for this little recess here. Okay? And also shows you here the typical widening of the joist, okay, at the base for about 3 feet. Okay? So depending on what you need, right? For 30 inches, you will increase 2.5 inches on each side. For 20 inches, you will do 2 inches on each side. Okay? And so those are typical details for joist construction. So I'm showing you that. Remember, you have to have a continuity bar. This one bar has to be continuous. Okay. Oh, bar cutoffs. We haven't discussed this yet, but that's when you cut off a bar that you don't need, right? So I mean, if I find that I need 2 bars for my maximum positive, that happens only in the middle. At the edges, I don't need that bar, so I may need to go from 2 to 1. Right? So that's your bar cutoff, but we haven't done that yet, so we'll see that later. Mm-hmm. So here show you some bar cutoffs. Okay, so you cannot cut the negative value. You need at least 0.25 or your length before you cut it. Okay? And here you have 2 sets of bars. One has to be 0.3, the other one 0.2. Okay? And each depending on the span. Here in the middle, remember you had to have at least 1 continuous bar, so you had to splice it, right, in there. And so this one right in this direction then is your joist, right? And these are your beams. These are your main beams. And this is your slab. And this white part right here is your joist. Now there is no difference, right? Normally when I was doing the sketches, I was showing a little difference, so that way you can see it. But really remember that the joist and the beam had the same depth, so there is no difference. Okay? But this one is a joist. This is one span, this is another span, this is another span. Okay? So these spans are like 30 feet, 30 feet, 30 feet. Okay? So that's what you're looking at. Right? And there is no difference in height, simply because, as I said, the joist and the beam, right, have the same height usually when designing beams, designing joists. Okay? So you need to anchor the bar at the end, either using a hook or a headed deformed bar. We're going to see that later in the design of splices. Mm-hmm. And it has to be continuous. Okay? So we have that. Mm-hmm. Okay, so let's start with a design example. Here again, here is the joist. Okay, and you are looking at this, right? So the length of the joist here like that. So this is 21.5, 24.5, 24.5. So if you look at the elevation, is this one, okay? 21.5, 24.5, 24.5. Okay? And it continues. Okay? So it continues. So you have that joist system. This one right here is your distribution rib. Okay? So the joist, right? Distribution rib. This is a standard joist with a clear spacing of 30 inches. Okay? Your beams are 1.5 wide, right? In there. So center to center is 23. clear value 21.5, center to center 26, clear value 24.5. Okay. So we have in the system standard joist. We got the center to center dimensions. The live load is 80 psf. The additional superimposed dead load is 20 psf. There is the strength of the concrete, the strength of the steel, and we're going to follow ACI 318. Now, normally we design this by using the moments and shear coefficients. Remember the shear coefficients that we have already, that you have already used in your project, right? So first, let's start with this slab. According to the code, it says for a 30-inch type joist system, 1/12 of the spacing, clear spacing, or 2 inches. When I give you 2.5, 2 inches, I said, well, let me try 3 inches. Now, you use 3 inches, this will need some fireproofing, yeah, because we already discussed this, right? That we need a thicker slab. If you have it exposed, you have a thicker slab. If you look at you go by the tunnel in the engineering, by the engineering building, you will see some of these joists with some fireproofing in there because of the thinner slab. Okay? All right, so the slab weight is here, right? And of course, by the way, the fireproofing has to go into the superimposed dead load, right? So that has to be there. It's a load. Okay, so slab weight then 3 inches, that's only 37.5. You find your WU, so your weight of the slab, and you superimpose the load, and then your live load, right? And that gives you this value. You just round it to 0.20. For the slab, because it's only 30 inches, remember the coefficient said that for slabs, right, that were very short spans, you can use 1/12 WU ln squared, ln being the clear value. Okay? And the clear value is 30 inches. Okay? We change it to feet here. And so we got then a moment per foot that is pretty small. What most people do is you design this as plain concrete, plain concrete, and you put your temperature and shear reinforcement, unless you have some really concentrated loads that you really need to take care of. So where is this formula coming from? Section 14 in your code. That is plain concrete. Okay, so plain concrete here, section 14. So this is when you design plain concrete. So it tells you where to use it, right? On that, members in building structure. So we got that. And let's go down to where the formulas are. You see. Design strength. So we're still satisfying the same requirements as always, right? But the difference here is the formula, of course, right? Oh, the P factor, by the way, is in 21.2, right? That's 0.6 for all the cases. So there is no different phi factors for shear, for bending, for column. No, there's one value, 0.6. Okay, and so here is the formulas for flexible design. You have to check the concrete part, which is this is your tension capacity of the concrete 5 square root of F prime C. Okay, and this is your maximum compression, right? But maximum compression is usually okay. The problem is the tension, right? You got that issue. Now notice that. Remember we discussed in what it was chapter 8. Yeah, chapter 8. I think we had chapter 7, right? Chapter 7 we had that modulus of rupture, right? The 7.5 square root of F prime C. That was the approximate or a measure of the flexural tensile capacity of a member. Okay, here, notice they're using 5, not 7.5. And so that means they want to be conservative in the design. Okay? So that's a 5. SM is the elastic section modulus. That one is exactly what you have learned in, hopefully, in mechanics of solids. Okay? So that's your moment of inertia divided by the distance to the maximum stress, right? Excuse me. Okay. So this is the formula then we're going to use. Okay. And so there it is. And again, the modulus will be this one, right? Because it's your moment of inertia, which is 1/12, right? BH cubed divided by the distance from the center to the maximum stress, that's h over 2. So you have then 1/12 BH cubed divided by h over 2, that gives you 1/6 BH squared. Okay? So that's something you want to know. Okay? And so we replace everything in the formula. This is regular concrete, so we have a 1 here, 3,000 here. Remember this in PSI. I still got a couple of you, using KSI in that formula. I don't understand why. I've been telling you, always PSI, always PSI. Okay. All right. Okay. So there is the formula then. We replace the numbers, right? 12 inches wide. Why do we have 12 inches? Slabs, right? Per foot. So your width is 12 inches. So we got that. We got this value as your strength. The one that we need to have is this one. You just change the units to pounds inch, so we match, or we change this one to that one, whatever. But here we're matching, so we're good. Right? Plenty of capacity with just 3 inches. Now we're going to find the temperature and shrinkage reinforcement. That's the 0.0018, and we got this number. Okay, and this assumes welded wire reinforcement of 60. So here you have to be careful because sometimes welded wire reinforcement can have a strength of 75, 80. Okay. So from the table, there are tables like for that. There are tables for that. So this is typical what you will find, right? So there is the 60 and the 80. So we're going to do the 60. Mm-hmm. And so this is, for example, what it says. You have a 3-inch slab. You can use regular bars, and it will be number 3s at 18. And what this means simply is because the only reason you're using number 3 at 18 is because you need to satisfy minimum requirements, right? You cannot exceed that spacing, remember, for temperature and shrinkage. That was 18, right? And so that's why you have that. And then this is your welded wire reinforcement. So what does it mean? This number right here means the area of the welded wire reinforcement. But you will say, wait a minute, 6.5. That's pretty big. No, this is multiplied by 100. So the real area is 0.065. Okay? So that's good. So this is the area multiplied by 100. Okay? So that's what it is. And then this one is the space of the wires. Okay? Notice that it's 12 and 12, so that means this one is spaced at 12, and then this one is also spaced at 12. So really what you have is a square mesh of 12 by 12 with wires going in both directions with the same area. Okay? And so these are the typical things. Now, you could have welded wire reinforcement where you use different sizes. Okay? So here you're putting this one at 4 inches and then that one at 12 inches. Okay? And so that's where you have the difference. Okay? And there. So then this one right here, which is 2.1 at 4 inches is giving you really an area of 0.063. Why? Because to make it to 12, right, the equivalent to 12, because this is 4, the equivalent to 12, you have to multiply by 3. So they give you 3 and 6, 6.3. But remember, this is the area already multiplied by 100, so you divide by 100, it gives you 0.063. Okay. So how did you get this then? How did you get that? 2.5, because the spacing is 4. To make it 12, you multiply by 3. So there it is, 3, you get your value. Right? So really what you're doing is that ratio. Remember that we did for these labs. 2.5 is at 4, like x is at 12. Right? And you solve for x. Okay? That's what you're doing. Okay? So it's the same setup that we've been doing already for these labs. Okay? But notice the confusion, right? So now I have these things in different sizes. So what happens if I put this mesh the other way around and make all confused? And so that's why this is what we used to do, right? But now we do this. So the advantage of doing this is simply that now it doesn't matter. You just put your mesh, okay? It doesn't matter which way you put it because both have the same direction. Okay? So this one is 0.065 per foot. Okay? 0.065 square inches per foot. Okay? All right. And so that's what we needed. So that's what we used. Okay? Perfect. So that's this lab. You're done with this lab. Design. That's what you need to submit on the next submission for your project if you're doing joists. Now your joist design, we need to find some heights, right? So we look at the interior span, we look at the end spans, right? But why? Because we have, right, both end continuous. The end span, that one is, I would say, you have a little moment here, but it's very small. Remember, this is the 1 by 24th. So it's not really a very big moment. So I would say yes, one end continuous on that one, okay? And so that's why we have these two formulas, right? You get, in this case, it happened to give us the same numbers because of the lengths, right? So I say, okay, I will use 15 inches. So here I don't have to add any 20%. So just pretty much whatever we got. So 15 inches. And so my joist now then is 15 inches. I'm going to use 5 here because this is a 1 inch per 12. Oh, I match here with 3 inches my slab. This is 1 foot. So that means that here at the end, I had to add 1 inch and another inch. So I got 5 and 7. Okay? 5 and 7. Okay? And so to find my weight of the joist, I need to find the area, right? The area of that joist. And the tributary width, because remember the clear value was 30, right? So 30 plus 2.5 on each side gives me 35 as my tributary width, right? So that's my tributary width, right? Because the clear spacing was 30, and 2.5 and 2.5 on each side. And so now I need to find the area of this shape, right? And multiply by the gamma of concrete, and that will give me the weight of the joist, including the slab. Okay? So here it is. Okay? 1/2, 5, 7, so the trapezoid, right? Multiplied by the height, gives you the area of the trapezoid, and then here is the area of the rectangle, 35 by 3. Okay? So area of trapezoid, area of rectangle. So multiply by the gamma of concrete, you get your weight of joist. Okay. The load on the joist is going to be the something was not right here. I look at it and I said, I didn't correct that. Okay. Yeah, there is something not right. Then we're going to change everything. Wow. Oh, no, we're okay. I thought we're doing something else. Okay, sorry. Yeah, for a moment I thought we were doing something different. Okay, so this is it. So we found the weight. Okay, there it is. So I multiply by 1.2. Okay. So that's my weight of joist and slab, right? So I got then the dead load of my member. Now what I'm missing is the dead load that this member is carrying, right? And the ceiling material, mechanical, electrical, the flooring system, all that, which is my superimposed dead load. So here's my superimposed dead load, right? But that has to be multiplied by the tributary width, which is 35 inches divided by 12, right? So that's superimposed dead load times tributary width, again times 1.2. So those are dead loads. And then my live load, that goes also within the 35, will be 0.080 times 35 divided by 12. Okay? So then this is now my uniform load on the beam. And with this, we are going to find the moments and shears. Now, do not forget that this is a continuous member, okay? So this is one span, 21.5 clear and 23 center to center. There's another span, 26 and 24.5 clear, and so on. But they are all these spans. Okay? So we're going to do this continuous beam using the coefficients. And what I showed you here, because of the cut, notice this. So it is continuous, okay? I'm just showing you the first span. So this is just the end span with a clear value of 21.5, right? And these are the envelopes. So this is where the graphs that you were supposed to give me in your project submission, right? For envelopes, that's all. There are ways to find this. There are some references on how to find the location of these points. This point not critical, okay? You just need to know that they're envelopes. Okay, so my shear on the left, remember, is 0.5. So it's 1/2. That will your ULN. So load, length, times 0.5, you get your value. Right? The one that's here is this one, right? This is the one that is different. Is the 1.15 times that, 821. My moment negative on the left is the small one, the 124. On the right, I get 1/10, right? And notice that for the right, I have to use the average length to calculate my negative value, right? Because, right? Because I have two different lengths, right? 23, 26, 21.5, 24.5, right? So I need to take the average of these two, right? And use it, okay? And so that's what it is. The average of these two lengths, the two clear values, the average is 23. So then I use 23 to calculate my negative moment on this side, because this negative moment is affected by the left and the right. Okay? And so that's why we're using the average value. Okay? So here I'm showing you the use of that average condition only for negative moments. My positive moment will use the same span length, 21.5, and then give me my positive moment. Okay? The negative moment on the other side, that one will not really control, so we are going to skip that one, because this is already 1/10 and this is 1/11, right? So it doesn't control. All right, so that finishes this span. So this is what you have. Notice that I have plotted this one on the tension side, so that may look a little reverse for you, right? But that's all it is. This is being plotted on the tension side. And I already explained to you that pretty much the rest of the world plots on the tension side. Okay. All right. So, and by the way, I mean, when we take the pre-stress class, you take one of those, this is better than the other plot because it helps on pre-stress a lot. It also helps to see the shape of your tendons or your wire that you push for pre-stress. And pre-stress is going to offer next semester. If any of you wants to take it, I mean, it's available. You can register as an elective. Okay. All right, so we have this. Now we go to the other span, right? Second span that we have. The length was 24.5. Okay. So again, the VUs are both the same. So we get the value. Notice that this is 8.13, right? And this one was 8.21. So it was a little bigger because of this 115. All right. Even though the span was smaller, because of the 115, it got to be bigger. Okay. And then your moments, right? It will be 1/11. And again, we are using the 24.5 here, okay, which is this one, the 36.2. So this is really your third span. Okay, that's why. Okay, I was looking at that. So in other words, go back. So this is the first span, this is the second span, this is the third span, right? So I found the moments here, and the moment here was 1/10 of the average length. The negative moment here, right, is going to be 1/11 of the average length. Well, 1/10 is going to be bigger. So that's why I put a note that I didn't calculate that value. Okay? The positive moment here is going to be the same as the positive moment on the third span. The negative moment here is going to be the same as the negative moment here. So that's why I didn't calculate anything for this, but I went and calculated this one. Okay? Now, if the spans were different, then I had to do all three. Okay? So always trying to save time, right? I mean, you're always trying to look at what you don't need to do. Okay? So this is your third span. Maybe it should bold it. So that we even see that third span, right? All right, so it's the third span. Good, so your negative moment then left and right the same, positive moment in the middle, 1/16, your shears. Okay, so this is what we need to use for design. Okay. In there. Minimum cover, 3/4 for joists. Okay. And just for the purpose of illustrating things, I'm going to use two different sizes of bars. But typical, I mean, you will use probably the same size on both top and bottom, right? And so you will have then a number 5 here at the bottom, number 4 on the top. So that gives you a little different D's. I mean, you can see that it's not significant, right? Your A value, hopefully someplace here within the flange, so you don't have to do a T-beam section, right? This still works the same as your C and T and your D minus A over 2, right? And then here, your A value, notice that it's creating a trapezoidal figure. You can find the area of the trapezoid, but in most cases, we kind of take an average, all right? And do that. And you say, well, wait a minute, but an average, why would you do that when you find the actual area? Come on. I mean, you know, the formula for trapezoid, right? I mean, we just did it here on the weight. So what is this? 1/2 of 5 by 7. That's the average, right? So really you're doing the average times the height. That's what you're doing. So, yeah. So it's just the average times the height. So the average of these one and that one, right? That's 1/2 of 5 plus 7. Multiplied by the height. So we are using an average, so we're making an average rectangle. right? That's what it is. All right. So there are the different D's being calculated. Notice there are no stirrups. Okay, no stirrups, right? And so you have to use that, no stirrups. Mm-hmm. Okay, let me open something here for you. Design 8s right here. Design 8s. Mm-hmm. So those are your, let's see what I'm trying to do here. Oh, yeah, I remember. Okay, so number 5, it has an area of 0.31. And so I always get that question, and I don't know, you've been asking that question. So why are you using 0.31? So it's not the area, okay? What happens is that the diameter is pretty close to 0.31, right? Is 5/8 divided by 2, which is 5/16. And that gives you 0.3125, right? That's too many decimals. So we just use 0.31. And so that's why the 0.31 here is not the area, it's half of the diameter of the number 5. And this is half of the diameter of the number 4. Okay? So don't make that mistake, okay? This is half of the diameter. Okay, so no significant difference really between the two, but there we are. So interior span design, we are going to pick a moment for the positive. Okay, so let's look at that, okay? So we went with a positive moment here, 21.9. Positive moment here, 24.9. That's the largest on this span. So we're going to start with that one. Okay. Start with the design, regular formula. So here is the formula that we've been using with the phi factor of 0.9. This d minus a over 2, remember, we always replace it by 0.9d. Now I'm going to do an improvement here. Because the slab is so small, you only got 3 inches. A 0.95d gives you a better estimate. But you can do 0.9d. I mean, you're still going to get the same answer. The only thing is that here I don't want to do a one more iteration. So by doing 0.95d, I know I'm very close. Okay? So my AS then is 0.42. I still need to do this thing about the effective flange width. So we have to use, remember, 3 formulas for the effective flange width. Okay? And in this case, out of the 3 formulas, the center-to-center spacing controls. So your effective flange width equals your tributary width. Okay? Remember that, okay? Because sometimes I put it in the questions on the part 8 question, right? Could the effective flange width be larger than your tributary width? The answer is no. You can go past the tributary width, right? So the maximum width for an effective flange width is the tributary width. Okay? So that one controls 35. All right. So I got that, my AS. I find my A value, very small as you can see. So that's why, I mean, you don't make much errors we're doing here. Definitely is within this slab, is rectangular. What that means is now that the B of 35 inches is correct, right? Okay. You get a bit deep thing, you have to go into T-beam design. Okay? But that should not happen. Okay? That should not happen. So with that then, I'm going to check again my area of steel here, right? and I put it back again, put my 0.28, do a little calculation here to refine my value, and notice that it's 0.40. So not much difference between that and that. So I'm going to use two number 4s and 0.40. So we're going to use then two number 4s, no stirrups. I mean, there is no room really here for stirrups in this case, but I'll show you later how you can put stirrups. So B minimum, now we only have what? Side cover, right? Bar diameter, spacing between bars, the second bar diameter, and the side cover, no stirrups. Okay? So my B minimum here, notice that gives me 3.5. Okay? So that's why they specify this 4 inches, right? So you add, you put here, you change it to number 5s, you're gonna put it in 4 inches. Okay? You may put 1 bar, but not 2. Okay? So that's why that width needs to be checked. Make sure that you have the right width. Okay? So two number 4s, 2 number 5s are very close. After that, you cannot put. You had to put 1 bar. Okay? A lot of people prefer to put 1 bar. So one will do maybe a 1 number 6. Okay? Well, that's not 0.40. Let's see. We need a little bit bigger. Let's find out. Okay? So you put 1 bar, right? 1 bar. You are looking at 1 number 6. Okay? So you had to put 1 number 6 instead of the 2 bars. Okay? Right there. And there is a reason for preferring, to put 1 bar. And I will explain that later. So normally, most people like to have this instead of 4 inches, 5 inches, okay? Which then allows you to do a proper consolidation of your concrete. Okay? You need to add the stirrups. The joist width will need to be increased, right? Because now you have to add for the spacing of the stirrup. This is why, again, see, there's the reason. Okay, you want to put the stirrups. 1 bar probably be better, and you will use the number 6. See, I was ahead of me. Well, the example is going to continue with the number 4s, 2 number 4s. So we do that. Check now the actual A, the actual D, right? My C, my ductility check, perfect K, my row minimum. I had to do that using the regular formulas for beams. So I compare the 2 rows, right? Rows values that I'm providing, right? In there, and everything looks good, right? Wait a minute, this doesn't look the right. Oh, okay, I see what we did. But first, I think I need to change that one. Okay. And we also have this little guy, right? So the area then, and that, right? So let's go back, where are we here? Get 0.40, nothing, all right, 0.40, right? So we're putting 0.40. Yeah. So we're putting 2 number 4s. So that's 0.40. Okay. So 0.40 then divided by 6 and divided by 14. And for those that are reading the notes, right? 2 zeros, 47, 6. So this is okay. This was wrong. So the B that we're gonna use was the 6. So I use kind of an average of the B because we got to remember 4 and 7, right? So that's 11, 5.5. So I said, okay, an average. Mm-hmm. And so that will make my value even smaller, but notice that it's still higher than my minimum. Okay? That's kind of conservative. In there. Now I find my capacity, 25 versus 25, so we're good. Okay. Exterior span, that's where we got that moment of 24, right? We're not going to design that one, right? Because, I mean, we already did this one, and that's already covered, right? So we know that this one right here, this one right here carries 25, so why are we going to design for the 24? We use the same, right? So this one will carry that one too, so we use the same. Now the negative though, the negative is a little higher, so that will not work. So the two number 4s will not work on the negative, so we'll have to do something else. So we'll do the same, make it quick, find the area, right? Now it's 0.64. Now here, right, is the other way around. If I assume again an average, so here we're going to do that average, right? But why 5? Because now we're looking at the A. So I'm looking at these. I'm not looking at the whole thing, right? An average B through the whole beam is just only this. So you may go from 5 to maybe 5.5. So he said, okay, conservatively, we're going to ignore the trapezoidal, right? Because now we're going to make it only 5. So we make it a rectangle of 5. And that will be conservative because your area will be smaller, right? The rectangular area at 5 will be smaller than the trapezoidal. And so it will be a conservative approach of your C value. Right? But if you want the exact value, you have to use the trapezoidal formula. Okay, so we do here then 5 conservative. The true value is larger, right? And then if we do an average width, right? Now I said, okay, well, that's approximately maybe 3 inches deep. So notice that the actual value will be 525, maybe. Okay, very close to that. So we can do an average value. You get a smaller A. And with that, you check your area of a steel. And that's 0.64. We check our minimums. And so A is minimum is satisfied. Again, here I want to make my requirement of the A is minimum bigger. So I make an average of the whole thing using 6, right? And that's 0.28. And we're putting 0.64, so we're good. Right? So notice how we play with this width, right? If I want less compressive force to be conservative, right? I make the trapezoid a rectangle with a smaller width. Right? If I want to provide the requirement for A is minimum to be bigger, I increase the B, and that gives me a bigger A is minimum. All right. So now we check for our ductility, and A is maximum, that's satisfied. And what happens next? The problem here is this is now bars on the tension side. According to the code, remember, you had to check for that L and over 10th, right? And spread your bars on that location. And most designers will not do that. They will put the bars right in the middle and add extra bars on the side because people can dig holes through this. Okay? And so, but we're going to follow the code, and we're going to use the Ln over 10. So maximum distribution length, 24.5, that's the span. Click span, divide by 12, divide by 10, that's 29 inches. So out of the 35, you need to cover 29. So that's less than 35, so we are going to put our bars within the 29 inches. And so we say, okay, 4 number 4s each are 9 inches apart. So plenty of bars in there for cracking control. You cannot use spacing more than 12 inches for grade 60. Remember, you cannot exceed 12 inches, so that's good. Cracking control satisfied. So as I said, I mean, because of the cuts, right? Most people will do one number 8, boom, right there in the middle. All right, that's done. Okay, and then you will use extra bars coming from your temperature and shrinkage. Okay, and that's a much better design. All right, so there is the other moment, the 12.8, right? Okay, well, let's see what happens to this one. So we get an area of 0.23. We again find our A value, find a B average. To do that, find our area of steel. So it's less than the raw minimum. So we have to use raw minimum. And so it's 0.29, right? So again, maximum distribution, the length of the exterior span is only 21.5, so you need to cover 26 inches. We say, okay, well, spacing, you use this number of bars, right? The spacing comes at 18. We cannot do that. We have to use 12 because of cracking control. So the lowest, the smallest we can use is number 3 bar, and it had to be at 12 inches, right? And that covers 24 inches. Okay? So we are a little low here. So what happens if I do now 4 number 3s, right? That give me that. So that will be each at 7 inches, right? And that will cover 27 pretty much. Okay? So 27 inches will have that. Okay? Okay. So 4 times 7, about 28, close to 28, but because the diameter is exactly, 27. This one is 3, right? But you only got 2 spaces here, so that's 2 spaces, 24, so you don't get more than that. Okay, something in the right here. Let's see. This one is 3 bars. So you got 2 spaces. That'll give you 24. This one is 4 bars. If you put 7, that's only 3 spaces. Yeah, that would be 21. Oh, so this should be 9, not 7. Okay. So because 4 bars will give you 3 spaces, so you're covering a distance of 3 times 9, 27. Okay. So you follow that? You got 3 bars, you got 2 spaces, each at 12, so you're only covering 24. Here you're going 4 bars, you got 3 spaces, each at 9, so you're covering 27. Okay. Okay. So again, we did that following the recommendation of the code, or you can use one number 5 right in the middle, and you put temperature bars extra on the side. Okay. And this is the more practical solution that you will find in actual designs in the field. Okay. Shear design, we pick our largest value here. That's the maximum value that we find. Okay. The code allows us to find the shear at a distance d from the face of the support. And so now I'm going to find then that shear at a distance d from the support. So all I have to do is take the shear that I found and subtract the load at the distance d. All right. So let's go here to this figure. Well, we're doing this one, right? So here we go. So this is the largest, and I want to find the shear not at the face, because remember this is clear distance, so not at the face of the joist, but at the distance d from the joist. So what that means is it will be the shear force that we got here at the face minus the load that you have on a distance d. Okay? So force minus that. Okay? And so we have then that value okay, so 891 load times distance d, 744. Here we're not providing reinforcement, so we had to use, remember, the formula with no stirrups. So we had to do so we need to know this rho W, right? And so rho W, based on what we have provided, we got 4-number force that we decided to use in there. And so we got the rho W. We need to check for the size effect, right? And so we got a D value of 14 that give me the size effect. Normal weight concrete, so give me my value. That number is 5. This is now lower than what it used to be, so that's why I said people are looking now at these joists as a potential for some corrections. All right, so we find, and 520 is the V sub C, but the shear that we need to satisfy is 744. Oops, cannot do it. So let's use, remember that widening, that we can do the widening, right, on a length of 3 feet, right? And we can do that. And so now I'm going to find the width at a distance d of 14, assuming that I'm going to taper the width following the requirements that we allow during construction. So we do that, the width at 14 inches is going to be 806. This is just interpolation here pretty much, right, to get that value. So you know this value, you know this value, so you need to find this value here at the distance d. Okay, so by proportions, so we do that. So the value then is this, and that will give me now a strength, right, because we're changing, the only thing that's changing in the formula, well, kind of, not really, but close. So we have to still look it up. Yeah. It used to be this way where it was very easy, where you just do this ratio, and because you're changing the BW, right? So you make it 8 now, so your load increases by 8. But the problem now is this guy, right? What happened to this guy? This guy is also a function of BW. So theoretically, yeah, that's also being reduced. So really, what is happening then is that now we got, see now the formula, see the complication of this formula, it really got very complicated to use, because now the formula is non-linear on B and B and D. Okay? And so when you change one, you don't know what's happening to the other side. So let's do that rho W pretty quick here. That will be 0.80, right, divided by the new width, which is now 806, 8.06, divided by the 14. My rho W now is 0.007, so now I need to raise this guy to the 1/3 power. So I will do that, and I get, oops, 0. Oh, wait a minute, that doesn't look right. 8. Oh, yeah, this one right here. This is what we're trying to change, right? And so I'm getting that the value with the exponent already is 0.192, right? And this one that we have here, this one right here, is 0.0114, and so it will be so let me find that one. The square root of that one, as cubic root of that one is 0.0114, and that number is 0225. Okay, so the correct thing here is to do the following. So this one is, I don't like that one, and so let's do that one. But then here we need to multiply also by now the old rho W and that. So the new rho W, so let's do that. So rho W cube, right? Let me do this. Let me do this so you guys will remember. So this is going to be your rho W. Okay. So rho W, oops, not that big. Rho W. It's going to be rho W. You do that. And let me put it inside a parenthesis here. So we are going to put that. But this is going to be your rho W new. Okay? And then this one is the same that would be your rho W old. Okay. Oops, what is this? Oh, I did something wrong. Oh, it's copied the whole thing. Sorry. All I want is just this, not that one, just that. Okay, so that would be that one. We need to raise this to the 1/3, right? So it would be 1 divided by 3, and then the same here, right? That would be 1 divided by 3. And again, for those of you that like formulas, right? So you like formulas, this will be my BW new, right? And so we can just, oops. Come on. Okay, so we copy that one, put it here. And so this is my BW old. So notice the problem, right? I mean, this is the new on the top right here. So then this should be the old, right? Yeah. No, this is the new and the old. Yeah. And this is the old. Okay. And so if we do that, what is going to happen is we got then 5.20 times, so put that guy there, and then put this guy there, and it's going to be the new value, which is 8.06, divided by the old value, which is 5, right? And then we have to multiply also by the ratio. These are the guy. So we do the same. And what happens now is the new value actually got lower. So it's 0.192. And this one is 0.225. Okay. So I already found the numbers, right? So that's what we have. So really then is a little less than what I found there because of the non-linearity now between B and D. So we got then 5.20 times 8.06 divided by 5 times 0.0192. Oops, no. 0.192 divided by 0.225. And so it's, ooh, that's not good. See, that's what I was afraid of. Yeah. So it's not bigger than this. It gives you 715. So yeah, that's what is causing lots of problems now with the new code change. So it's not, because this value happens to be now 7.15 kips. Oh, yeah. So that creates a little bit of a problem there. Mm-hmm. So then it's not okay. So it's no longer okay. We need shear reinforcement. Okay. So we're going to do that. So it needs shear reinforcement. Okay. Okay. So we're going to put that. Needs shear reinforcement. So when we do the shear thing, the chapter on shear, we'll look at how to put shear reinforcement on this. What is this? There. Okay. So I was afraid of that thing right there. So that's exactly the problem that we're having with this new formula that they have put in the code. As I said, it was developed for regular beams, but they didn't realize, this problem. We're widening my joints, which is something that's been done in the past. It has worked very nicely for a long, long time. But now it doesn't work. Okay? So it's forcing you to have that. Okay, and then shear reinforcement, we'll discuss it in chapter 9. So typical details here that we need to put, remember using the 0.3 ln, the 0.2, so we'll use all those values in here, the 0.25, so you calculate that. So what you have, remember, this is now the joist, right? And these dashed lines, this one right here represents your beam. This one is your distribution rib, beam, distribution rib, beam. Okay? And these are your bars. And remember, one bar has to remain continuous, right? And there. Okay? And so that's what we have there. So don't forget that the graph that you're seeing there is beam, right? Joist, distribution rib, joist, beam, joist, distribution rib, right? Joist, distribution rib, joist, beam. Okay? So that's what we have, and I think I only show you one of those ribs. Okay. And because the beams and the joists have the same height, you don't see really a difference, right? But that's what you have. Okay? So that beam, your joist, your distribution rib, joist, and support. Okay? All right, so that's the end of this, and it took longer than what I thought because of what the corrections I've been doing.